I welcome everyone to this presentation. So today I'll talk about machine learning. I will go into the basic concepts of machine learning, and then we'll see how we can use some of these techniques, some of these methods for the wireless applications as well. So I'll try to give an example of one to two, maybe around 2, 3 as the time permits, research problems related to it as well. So, as ma'am said, I'm Rishemjit Kaur. So now let's start with the lecture on machine learning and AI. So, whenever we talk about AI or machine learning, what is the first thing that comes to your mind? At least this is what that came to my mind when I first heard these words and when I first ventured into the area of when I started my journey into the area of artificial intelligence, machine learning. I thought some killer robots like we saw in Terminator or like in a Matrix movie who are going to come and take over humanity. So this was my idea of machine learning or AI, but that's not how it is. This is not what machine learning is. So these days we hear a lot about artificial intelligence, a lot of machine learning and its different applications. We have heard that how AI can be used for social good, how is it tackling some of the biggest world problems, how it has the potential to solve economic or maybe poverty related some of the problems. And we are actually seeing its use in different medical and the agriculture applications as well. Like if I talk about agriculture, the simplest one that even you may have seen different kind of apps which are available where you can simply click a picture of a leaf or a plant and it tell you what kind of a disease a certain plant has, what kind of treatment it should be given. Then it is being used for like the plant growth monitoring, how much of nutrients should be added. So a lot of different applications where AI is being used in the context of the agriculture. Then the role of AI in healthcare, especially in the times of COVID, we saw that there were so many algorithms, so many applications which were trying to predict on the basis of different demographic, who are the people who are at most at risk, who are more susceptible to this, the group who should be protected based on some of the AI techniques. And we see that AI has helped us in like early detection of ailments, maybe on the basis of X-ray images, MRI images, and a lot of different sort of methods, different sensors as well. It helps to improve decision making. It can work as an aid for the doctor, can complement them and take off some of the workload from them for the by performing the initial level of screening. It can help in treatment. We have seen the usage of like somewhere at least the assistive robotics. Then there is like associated care. It also helps elderly in taking care of them. It helps to provide a superior experience. And these days we also see a lot of wearables coming up. For example, the Fitbit or our smart watches which can track our heartbeats and blood pressure and everything. And then we see that how they are being used to help in our healthcare. So these are some of the applications that we hear in our everyday life, that we think about it. But the thing is, what exactly is AI? Like, what is the formal definition of AI? So if I talk about the notion of AI, it is broadly understood as any kind of artificial computational system that shows intelligent behavior. Any kind of intelligent behavior, we sort of consider it that it is part of the AI. So that's a very general, very broad definition. And we should also keep in mind that our target is not to achieve an intelligence which is similar to the humans. That's not what we mean by artificial intelligence here. We do not even, in fact, wish to restrict its intelligence to what would require intelligence if done by the humans. They can have a very different sort of intelligence. They can have a very technical intelligence, in fact, the limited abilities as well. So we will talk about that just in one or two more slides. So then I think it is also important to know about the history of AI, how it has come into the being. So the very first time the term AI, it was sort of coined it was used in the Dartmouth conference in 1956. So after that, we had seen a growth in AI. There was also a very inflated hype around it. And based on all that, there was also a lot of investment and research into it. Then we saw the period of two consecutive AI winters, where there was not much of a growth. In fact, the enthusiasm of the researchers, it has gone down, and it happened consecutively for two times. In fact, it was in such a condition that even when the areas like natural language processing or data science or machine learning, they were coming up, they were not often labeled as AI, because they do not want to get the negative connotation with it. So, but since we'll say around maybe around 2000 2010, the usage of this term has again sort of exploded. Now we are again in the era where we are considering that the AI, the machine learning, it is the fourth industrial revolution. In fact, in towards 2020, we are in a stage where we are also concerned about the AI implications. We want to develop some sort of regulations to even control it. We are thinking about what if AI, what are the moral aspects related to it? Like, for example, if it should be transparent, if it should be explainable. So these are the recent trends, because we see that the AI will continue to grow, and in fact, it will create a lot of jobs, uh, lot of opportunities, and will contribute majorly to the GDP in the coming years. In fact, it has already created a lot of jobs, and along with that, at the same time, there are also concerns in the sense that, that the employment rate will go down. The machines, since they are going to automate a lot of the processes, they may take over the jobs of the humans. So some of these concerns are valid, some of these concerns again may be lot exaggerated. Like, we also saw that during the time of the industrial revolution, where people thought with the more automation, with the coming of the machinery, the jobs will go. But at the same time, it also created a lot more jobs. So that's what we hope from the AI as well, that it is going to create more jobs than actually it is going to take over. And we are even seeing that, there are different type of jobs in the sense of the social media. There are now social media influencers. Even if they are not technical, they are providing opportunities to many different people to come up. Now, coming up to, what is the reason that has driven this growth? So there are three major reasons which have contributed to it. The one, bigger data. We have so much of data which is available these days, which is being generated every day, every second, every minute, that we have never thought earlier. There is such an exponential growth. For example, we all use social media, right? So whenever we post a text or post a video or the image, we are generating data. Whenever we click an image with our mobile phone, we are generating data. Whenever we use a wearable device, and which is collecting our sleep patterns, which is collecting our heartbeats and everything, which is, again, we are generating data. And it is being generated at a scale which we never thought earlier. So having more and more data, it is also giving us the opportunity to explore it. Secondly, the increase in computational resources. Over the period of time, we have seen that now we have such computation in our own hands. For example, our mobile phones, they are so computationally powerful as compared to even maybe the laptops or the bigger computers which are available 10 years ago. We have more computational power in our own hands now, with the cloud computing, with the GPUs coming up. The access to the computational resources is limited to a certain few people. It has democratized a lot. It is now available to the researchers everywhere. It is now available to the general public. So since the availability of computational resources, it has enabled people to do a lot of different sort of data analysis. So that's another reason which has resulted in this explosive growth. And then the third reason is better models. So we have also, like, we started from very basic models, but now we are into the era now where we are talking about the deep learning models. We are talking about many other different type of computationally complex, computational intensive models. So it is the availability of better algorithms. It is the availability, it is also the understanding, more understanding of how the different machine learning techniques work, more awareness, which has resulted in this explosion as well. Like, more and more people are now aware how to use these models, and many companies, small startups, are adopting it. They are adopting it as part of their regular activities in itself. So Again, now coming to the AI, like as I was talking about, when we talk about AI, firstly we should not think that this is equivalent to the human intelligence. No. So we see AI, there are three stages: narrow AI, general AI, and super AI. Now when I talk about narrow AI, it is like something which is dedicated to assist over with specific task. For example, let's say we see bees, right? They are very good at collecting honey. They are very good at in those honeycomb sort of a structure, making that. Whereas birds, they are very good at making the nest. But can bees perform the same task as birds, or the birds perform the same task as bees? No, that's not possible, right? So they are they have evolved, they have been trained to do just like they're good at certain specific tasks. And this is what the concept of narrow AI is also, that all the in that it accomplishes specific task only. In fact, all of the AI that we see today around us, they belong to this category. They are narrow AI in itself. They are very good at doing one task, but when it comes to generalization, they're not so good at it. For example, we hear that we have developed the AI, to play chess, or to play games like Go. We heard about Google's DeepMind, and it has even sort of beaten the world champions in those games. But they are only trained for that specific game. Even if we try to use it for another game, they may not perform as well, or they may not perform at all, right? So the biggest thing that the narrow AI misses, the biggest characteristic, is the generality. So but whereas humans, they are very good at in generalization. For example, like we can write, we can read, we can jump, we can sing, we can do so many different tasks. And sometimes we also take knowledge from one domain and we transfer it to the another domain. For example, we see, let's say if we see a completely new thing, we we may try to categorize it on the basis of the past experience that we have. We may be able to look at it and say, oh, the length is this or the width is this. We have some sort of generalization ability, right? So that's what we hope in the future we will be able to get in the AI as well, that we will be able to get the some of this generality which humans have in the AI also, that it will be performant as a human in perception task. It might be capable of reasoning. Now the third stage of AI, that is the super AI, where we assume that machines that are even smarter than the humans. So I think that's still something very far-fetched, not something that we have at the time at this point. And it may also take us a very long time to even reach there, if that ever happens, right? So this is where we expect AI to perform as if all to perform better than as all the humans combined, that none of the humans would be able to compete with it. Probably that's what the Matrix or the Terminator is about, right? So now I have been using the term AI. I talked about the topic of my discussion is machine learning, right? So we hear the words like deep learning and then data sciences. How are these terms are all related to each other? It is very important to understand. So when I talk about AI, it is more or less, I'll say, a broad term, much broader term, saying that it tries to simulate human intelligence, any kind of human intelligence, right? So that's what we in general say the AI is. Now AI, as I said, it further has three different stages: the narrow AI, and then the general, and the super AI, right? General AI equivalent to human, super AI which is much much bigger than human. So this is the part that may or may not be our future. But what is present? That is the narrow AI, where we are good at doing specific tasks. And in this narrow AI, the one part is machine learning. machine learning, where we give this ability to the computers, to the algorithms, where they can perform the certain specific task without using, let's say, any explicit instructions, where they learn on the past data, where they learn some sort of statistical patterns found in the past data, and based on those patterns we try to predict what will how an unknown sample should also look like. Sorry. So for example, uh, let's say a machine learning model that is meant to detect automatically an animal species will learn from many images, millions or thousands of images of animal photos, that the maybe the the cat ears are pointy, or dogs have this kind of tails, and this animal doesn't have a tail, or something like that. So that's how it tried to look into the patterns. Sometimes it is on pixel to pixel basis, and based on those patterns, based on those features, it tries to learn. So we will talk more into the details of the machine learning. And a very specific area of machine learning is what we call as deep learning, which are deep neural networks with many hidden layers. This is the area which has sort of exploded in the past few years, and a lot of I'll say that the advancements that we have seen in the area of machine learning in almost the past decade, it is related to the deep learning itself. Deep learning is somewhere where we do not specifically have to provide, you can say, the features to the algorithm. We do not have to do the feature engineering, but this is where the algorithm learn itself from the data what should be the features. And because of a lot of computational power, as I discussed earlier, which is available, deep learning has also become possible and more accessible to everybody. So but in this talk, in this lecture, we will keep our focus on the basis of the machine learning itself. So now coming to the machine learning part. So the more formal definition, when we say what is machine learning, it is a field of study that gives computer the ability to learn without being explicitly programmed. Or you can say it is the study of the algorithms that has three parameters: P, T, and E. P is performance. T is some task where we want to improve its performance. And then E is experience, which mostly in this case, we call it as the data set that we have, like the past examples that we have, some sort of historical data. So a computer program is said to learn from its experience E with respect to some task and the performance measure P, and we expect that the performance will improve over the time period by learning from its experience, by maybe even the improvement in the experience itself. So you can, like, if you want to relate it, you can say it is very much similar to that of the humans itself, right? The way we learn, like when if you will observe, like we also learn from our past examples, right? Our past experiences. If we see that let's say touching a hot pot, like if we touch it and we see that, okay, we got some experience, this should not be done in the future, so in future we will also avoid touching something like hot surfaces, right? So we learn from our experience. It is, you can relate the similar way we expect that the machine learning also behaves. It also learns from its past experience, from its past examples. Now, how machine learning is different from the you can say that the traditional programming. Generally, like, people say, okay, like without explicit instructions we can also code a certain task. So what exactly is machine learning, or how is it different? So giving you a very simple example here. In the traditional programming, what we have is, we have input, then we have a certain program, that is a certain set of instructions, which then we get certain set of output. For example, the input is 2 and 3, and our function here is to perform the addition on that. Then our output will be 5. 2 plus 3 is 5, right? But in the machine learning, it is a bit different. It is different in the sense, we have input as well as output. The computer itself tells us about the program. It tells us about the relationship between this input and output. For example, in this case, We tell them that the input is 2 and 3 and the output is 5. So what will be the relationship between this input and output? So the machine learning is supposed to tell you that there is an addition relationship between this input and the output. So that's what the machine learning is. This is how it is different from your traditional coding or programming in a very simple measure. Like there are also very complicated tasks that we provide, that we do with machine learning, but this is a bit of a simplification for the understanding. Now, the question is, do we really need machine learning, right? There are so many problems where people sort of sometimes also overestimate that if we need machine learning or not. Like a simple example that I ask almost everyone whenever I start with the machine learning, that let's say I have a machine where its purpose is to count the number of coins, right? Like for example, we go to the banks and we see those machines where they count the notes. Like the bank person, the teller will simply put it in like a pack of a bunch of notes, and that it will count it for you. So do you think for such kind of tasks we need machine learning? Anyone from the audience, please feel free to answer if you want to.
Any participant who want to respond to this question?
Yeah.
Ma'am, already the ATM machine is doing that work, right?
Yeah, exactly. So do you think there is a machine learning at the back end?
No.
Yeah, exactly. There is no machine learning there. It's
Yeah.
asked to count it.
It is not learning from its any previous experience or nothing like that.
Yeah, exactly. So we don't need machine learning for all the tasks. So when do we really need to use machine learning? Now that's the question.
The real-time events, when it has to handle the real-time situations, the different situations. So from the previous experience, it has to take the immediate decision without any human interference.
Yeah, you are absolutely right. When it can learn from its past experiences. So there are certain cases that we sometimes describe. For example, where human expertise does not exist. For example, navigating on Mars. We have heard so much about the rovers, right? Now, no human has ever been to the Mars. So
Even the driverless car also an example maybe.
yeah, exactly. So driverless car, you can say, is an example where we have so much of data which is available. Driverless car is something which is like full of sensors, so many sensors, and it is definitely not possible for any human to interpret that data and do it manually. So we need machine learning over there. You have given a very wonderful example, ma'am. Any other example that you may like to point out? Okay, so we'll go ahead. So there are also sometimes cases where humans cannot really explain their expertise. For example, speech recognition, right? We all talk to each other, but can we really tell how we are recognizing somebody's speech? Can we talk about in the sense of the frequencies or its amplitude? No, we cannot, right? We don't know. We just have this ability to recognize it, but we do not know how we are doing it. So there are many such expertise that we have, that which are where we cannot exactly tell us what are the rules over there which define that expertise. So when we do not know that, then how do we impart that capability to the machine itself? That also becomes very challenging, right? So this is where the machine learning comes into play. So you can think about it in the same way as like when we teach a kid to speak a certain language, right? Kids learn it from their mother. We call that they know how to speak their mother tongue. We do not explain them any rules behind it. We do not tell them that a and the this is how it should be used. They just learn it. They just learn it from their environment. They just learn it from their parents, from people around them. So that's the another example where we learn it on the on our past paper, and we improve as we keep getting more and more data about it. Then there are certain cases where models must be customized. For example, the case of the personalized medicine. Now, in case of personalized medicine, now every human being is different. They have different diseases, different genetics, different lifestyle, different food habits. So the one medicine which may work for one person may not work for another person, another community, or a race altogether, right? Because there are certain genetic differences. So is it physically possible for the doctors to go through each and every sort of data which is available and then do it? No, it won't be. So this is where the models comes into the picture. Machine learning comes into the picture, where we can provide sort of assistance to the doctors, to the healthcare workers for such kind of areas. Then there are another examples where models are based on huge amount of data. For example, one of the example was given by ma'am here. For example, the driverless cars. Now there are so many sensors which are deployed on it. There is there are cameras, there are proximity sensors, and it is not possible for somebody to look at all of that data all together like at one point and take decisions so quickly, right? There are terabytes and terabytes of data which is being generated. And the similar another example is of genomics. There is so much of biological data which is being generated that it is at a very different level, at a very different scale. So this is where the machine learning comes into the picture. This is where machine learning helps. So we will see now very few examples where the machine learning has been used, or where the machine learning has learning from these examples, even the algorithms have been developed. So the very first example is the handwritten letters recognition, character recognition. So here you will see there are all the numbers from 0 to 9. And if you will notice that some of them are so difficult to recognize, even for the humans. Like it is so difficult to say which one is 2. Like the ones which are all here, these are all the examples of 2s, right? Even I cannot tell. To me, this one looks like bit like a 7, but these are all the examples of 2s, right? So and this was one of the first few examples where the machine learning was used to train and develop different algorithms. So it's a very standard, you can say, a textbook sort of a problem that every time we discuss. Then we see machine learning examples in our daily life as well. We all use Google, we use Gmails or Yahoo mails or different sort of mails, right? And there we have this little folder which is labeled as spam, where all the emails which are spam, which are asking you for money or want to be friends with you, they're put over there, right? So there are machine learning algorithms behind which can tell the difference, or which learn from the given examples and see what is spam and what is ham. In fact, sometimes the data collection in itself is a challenge, in the sense that how do you know a certain email is a spam or not, right? Either it has to be read by humans and then say, okay, this was a spam email. Most of the time that's how the data collection is done. Sometimes we can use some smarter strategies, like some of the researchers specifically for this very example of spam and non-spam emails, what they did, they just created some email accounts on Gmail, I guess, or any other mail service, and they never use those accounts. So whatever emails were coming into those email accounts means those were spam, because they never used those emails for communication with everyone. So that's how they collected the data for the spam itself. Then some of the other examples of machine learning that we see, it is the machine translation. And we have also noticed that in the recent time, it has become a lot better than what its performance used to be earlier, right? So if we want to translate it from English to Hindi or Hindi to Punjabi, there are so many different translation options which are available to us. Though sometimes it doesn't do as good as a human, but still it helps us when we are stuck in a foreign country and does not know any of the language. But still there is still a lot of scope in this particular area, because there are more than like 7,000 languages, and we hardly have been able to sort of record or perform such kind of translation for a handful of languages. So this is another area which is very which has captured the attention of the researchers. Then we see this, when we go to the search engines and it starts autofilling our options. For example, if I say Priyanka Chopra is, it will give me the options from which state, Miss World, isn't it romantic, all those sort of different options. So this is also where the machine learning is coming into picture. Then another example, for example, recommendation engines. We all watch Netflix, Amazon Prime, or Hotstar. We watch one movie and it will give us recommendation of 100 others, where we can, these are the movies that you may like. And you will see that as you watch more and more, as these engines, they get more information about your behavior, more information about your likes or dislikes. Their recommendations might also improve with time, because their algorithms, they are also learning with more and more data that you are providing. So this is, then there are some other examples now, as I was talking about the games such as AlphaGo, where the Google DeepMind has uh, like even perform better than than its human champion which was there. Then we all have seen the videos of the Boston Dynamics robots, where there are these robots which can, like, even if you kick them, they can get up by themselves, they can maintain the balance, or they can handle the things. Then there is a lot of application of the machine learning in the manufacturing setup, in the automation of the processes, like picking up of things, folding. It is actually happening right now. This is where a lot of robotics in the manufacturing is already happening. So then we have already talked about the examples of the of the driverless cars. Now, as I was talking about the biological data, the biological data is available at such a scale. Like we say that DNA, it is a storehouse of genetic information, right? It is a long thin molecule, two strands which curve around each other and forming a double helix. But if we just look at the scale at which this data is available, we'll realize that the DNA molecule in a cell, if it is fully extended, would have a total length of around 1.7 meters. But if you wrap all the DNA that you have in all of your cells, you could reach the moon 6,000 times. So that's what the scale of the problem is. That's how big this data is. The simple ATGC, ATGC, they generate such kind of data that we cannot even imagine, or impossible for us to handle it manually. Then the another application, which is the wireless networks as the data source. Now, for example, we know about Internet of Things, right? IoT, which is like a network of the physical objects, which is not just limited to the devices, but there could be like vehicles, buildings, any item which is sort of embedded with some sort of electronics or sensors, and which has network connectivity, any object which can collect the data, exchange the data. So there is so much of data which is being generated these days by these IoTs, by these IoT devices, that that machine learning is required to make sense out of it. Then there are processes like the network monitoring, which is a very critical IT process that tracks different network components, its endpoints, provide faults, performance, monitors traffic. It also involves like monitoring the critical network issues, whatever the fault detection is, maybe the health monitoring of the various network elements. So to do all that, to generate the charts and graphics and dashboards and reports, we have machine learning at the back end doing this. Then the another example could be the cognitive radio, which is a form of the wireless communication in which transceiver can like intelligently detect which communication channels are in use and which are not. So like in order to optimize the capability, optimize the use of the available radio frequency spectrum. So there are so many different sources. So when we talk about IoT applications, we see it in the further, like, the smart cars, the wearables, the smart appliances, smart buildings, in order to monitor the health of the buildings. Then smart homes, right? We all have Alexas and Siris at our home, Google Homes at our home, where we just want to tell them switch on the light or play a certain music, but they are all connected to a network. Then we have smart TVs these days also. I do not have any normal TV. All TVs are smart in my house. Then we have examples of smart farming, where we want to remotely control all the sensors, remotely monitor our farms, at what time they should be watered, how much of fertilizer should be added to them, or how much of light should be there. Then there is smart health. In fact, we are also coming up with the concept of making a whole city smart, right? In fact, this is one of the concept which is called as the smart world. Like in this concept of the smart world, we'll have sensors and everything which will monitor air pollution, be it the we already have stations which actually tells us what are the CO2 level, what is the emission from the like what is the particular matter which is which is there. Then how much of, then we may have something which may tell us how much of the pollution is being emitted by the cars or the toxic gases which are being generated. Then there is forest fire detection. Then there are so many other things. For example, what is the traffic congestion? Can we find out a better way to avoid the traffic? We are already using Google Maps to do that, right? But we can also imagine a world where we have sensors everywhere and it telling us, like, which monitors the vehicles and the pedestrians and try to optimize what should be the driving or the walking routes. Then we can have a smart road, smart lighting, which basically turns on or off based on whatever the weather conditions are, if there are clouds above or if it's a sunny day. Then there is intelligent shopping, where we can get advice at the point of the sale itself, and which tells us based on the customer habits, their preferences. So many things, even monitoring of the water quality or quality of the shipment conditions. So these are all the things that the researchers are imagining that our future might look like, if if in condition that we do not end up destroying the earth. That's a completely different situation. But that
One doubt, ma'am. If we make so much of things smart, so huge amount of data will be generated. So how that data will be handled in real time?
see, the things become smart because, one, there is some sensor which is collecting the data, right? But what makes it smart is not just that. What makes it smart is the machine learning behind it. Machine learning behind it to make sense out of that data. So if I talk about like the air pollution monitoring, or if I talk about the smart lighting, something which firstly captures the data and then some intelligence behind it, which tells to what actions should be taken, what sort of actuators should be activated, right? Which tells them that, okay, based on the sensor data, we can tell that it is cloudy today. Maybe the lights should be turned on earlier itself in the daytime itself. So actually, smart devices mean more data. It does not mean less data. Was
But
that?
how that huge amount of data is there already? Like in infrastructure, we need so much of memory handling.
Yeah, you're absolutely right. In the terms of infrastructure, we would require a lot. Like there are so many devices at the different end. They may send it to a certain server from the, and we may even have localized server, which may send it to some centralized server where like there could be the data processing, which is either being done at the cloud level or at the central level, or there are also edge devices. Like we don't need to do all sort of, the processing at one central location. There are some functions which we can itself perform at the edge devices itself, like at the level of the sensor itself. For example, if I talk about the smart lighting, so maybe some of the operations we need to send data back to the central server, but some of the operations we can itself do it at the at the end of.
Locally.
Yeah.
Locally, we can handle the things.
Yeah, but yes, you're absolutely right. It's not simple to make sense out of all of these data. So we definitely, at least at this stage, we definitely need a human intelligence behind it. For example, during this COVID time, there was this research coming up that in US they had those smart thermometers, right, where they check the temperature. So the temperature, it of course provides a local reading to the to the people who are doing it, to the humans itself, but it also sends data back to the server. So the data which they were getting from the different states, different parts of US, they could see that the fever, like on average, its trend, it would match with the at least give some sort of approximation with the number of the COVID cases, right? So the more people were getting COVID, more people were checking their fever, more people had higher fever, so they were getting this data. So yes, at least now we definitely need some human intelligence behind it to see what kind of patterns even we want to look at. Like this was one of the application which they never thought that they could be using it for, sort of to estimate how the COVID is spreading, or how it will be in the future. But they could see those sort of visualization, those sort of patterns from those thermometer data. So these are very interesting times, I would say. So much data being generated everywhere. So if any of you is interested, I would say that jump into this problem. So many so many job opportunities also in the area of data sciences, AI, and machine learning. And in fact, these days these are the highest paid people as well. Like some of the data suggests that. Okay, now again coming back to the like we have seen now many different examples. Now again coming back to the machine learning task, how we define. As I talked about, three different, you can say, parameters. Improve on task T with respect to performance metric P and based on the experience E. So let's say, firstly, our task is recognizing handwritten words, the one which I showed you earlier, right? So that's the task. So what will be the performance measure? The performance measure could be the percentage of words correctly classified, right? If you call 2 as 2, that is correctly classified. But let's say if your algorithm tells 2 as 7, it means it is incorrectly classifying it. So we can use the percentage of words correctly classified as one of the performance measures there. And what will be the E here? What will be the experience? That will be the database of human labeled images of handwritten words. Like initially there is some human being which tells that this particular word is 2, or it is 7, or it is 1, or it is 9, right? So that's the experience for that algorithm. Similarly, if I take another example, as I said, it's like categorize emails as spam or legitimate, spam or non-spam. That's the task. The percentage of email messages correctly classified, that will be our performance metric P, and the database of emails, some with the human given label, that will be our experience. So is if I take another example, third example, if we want to see if the tumor is benign or malignant based on certain set of images, then the percentage of tumors correctly classified will be our performance measure, and our experience will be the database of patients, which we already have. So when we say machine learning design, this is mostly how it looks like. So we want to find out what is the relationship between X and Y. This is the relationship that we do not know, some unknown target function that we want to figure out. For example, in the very beginning, I said 2 and 3, and the output was 5. So we could figure out it is an addition operation. 2 plus 3 is equal to 5. So that's our purpose. So there is some unknown target function which defines the relationship between input output, but we are not aware of that, but this is something that we want to find out. So let's say if it is a credit approval, like if we want to see if somebody should be given the loan, for someone credit should be approved or not. So there should be some ideal function there, right? But what we have is the training examples. We know that this was the input and this was the corresponding output. For example, if I again talk about credit approval, I know this was the customer, this was his behavior, this was his previous credit, like previous transaction record, and whether he was approved the loan or not. So these sort of training examples we have for maybe thousands and hundreds and millions of customers, right? The historical records of their credit. Then we have our learning algorithm. From this learning algorithm, we try to we try certain set of hypotheses. We try many different formulas which we think might be able to estimate the relationship. Like our actual purpose is to get as close to the target function as like get as close to it as possible. So we try a various set of hypotheses and we come up with the final one. Let's say we are representing it by G, which might be able to approximate our function F, our unknown target function. So this is the solution that our learning model helps us to achieve, learning model helps us to get. And this learning model, this is where the machine learning is, right? So there are certain steps to any machine learning pipeline. The very first step, you need to look at the bigger picture. So we will go through all of these steps through a example. So I'll show you an example, I'll show you the data, and we will go through all of these steps one by one. But just to briefly tell you what those steps are, the one, looking at the big picture, right? Two, which is the data collection. Like we need to collect the data for everything that we do. Without data, our machine learning algorithm will not work, right? We won't have anything to train on to. Then visualization. We generally try to visualize the data to get more understanding of it. Then data discovery in order to gain further insights. Here we try to use some sort of mathematical measures, some correlations to see if we can understand our data a little bit better. Then the next step is to prepare the data, like pre-process the data so it could be further used with the machine learning algorithms. Then we select the models, we train the model, fine-tune the model, we represent the solution, and finally launch, monitor, and maintain your system, which is mostly the deployment of our model. So we will start with this example of housing prices, right? So this is the problem where we want to estimate what will be the prices of the houses in certain area based on, let's say, where the location of the house is, based on how many bedrooms are there in the house. Let's say even if we go in the market and we want to buy an apartment, or if we want to buy a house, what are all the parameters that will define its cost, right? It may be its size, like if it is 500 square yard or 1000 square yard, right? How bigger it is, how many bedrooms are there, how many bathrooms are there, or what is in general the income of the people who live there. If it is like a certain area which is very posh, the houses might anyways be very expensive. If there are more parks around there, more swimming pools around there, the public facilities are there, the houses might be expensive, right? So this is the problem where on the basis of certain set of features, we want to predict what should be the cost of a house, right? So what is the bigger picture out here? The very first thing, we identify the task at hand, which is the very first thing is we look at the data. Now our data has certain matrices, for example, the population, the median income of the people, the median housing prices, and so on. The one particular data that I'm talking about, it is for California, right? So our purpose here is that we need to be able to develop a model which will learn from the data and able to predict the housing price in any district given all the input features, all the input variables. In order to frame the problem, one, we can have a business objective, because see, any machine learning algorithm, anything that you do, there has to be an end goal. Just building the model is not an end goal. That is probably just the starting of it, right? So we need to see how we can generate business out of it. How does, if company use machine learning, like why anybody should use it if there are no benefit to the company? So how does the company expect to use benefit from this model? It is very important because it will determine how you frame the problem, the algorithms that you select, what performance measure you will use to evaluate it. And sometimes your model's output is given as input to the another machine learning system. So there could be a downstream task as well, right? Which will determine whether it is worth investing in this thing or not. Maybe based on the, let's say the prices of the house that you predict, it will go into some another downstream of investment task itself. Then the another thing could be that there are already certain either models are available or it is being done manually. So we want to beat that, because unless and until your model does, what is the point of developing a new model if you cannot maybe beat, a regular, let's say a dealer or someone. So what is the current performance? What is to be beaten? That is also important to know. And as I was talking about the business pipeline, that sometimes your output, it becomes like input to the another downstream task itself. So for example, here you have some sort of upstream components, district data. Based on that, you predict what will be the pricing in that district. Now those prices, along with some other signals, it can go to the investment analysis. If somebody just want to, let's say, see what kind of investments should be done, so they can see, okay, this is where the one component, the prices is, rest of the investments maybe mutual funds, this and that, one is in the real estate. So it can become a part of another downstream task as well, right? So now the problem is, how do we frame it? So we understood what the objective is, we understood what we want to do. Now in terms of machine learning, how do we frame this problem, right? How machine learning, what kind of machine learning models should be used? So generally, in terms of supervision, there are maybe three: supervised, unsupervised, reinforcement learning. Then there could be classification, regression, or maybe something else like PCA, dimensionality reduction. Then it could be used in batch or the online learning. So we will learn about all of these things in the next few slides. So when I talk about supervised or unsupervised learning, now as the name in itself suggests, it has something to do with supervision, right? Supervised means there is something to guide. There's somebody to supervise. Now, what that means in terms of data is, you have known data and known response. Like, you know what is the input and you know what is the output. You already have a certain set of data like that. For example, when I talked about the predicting the prices of the house, I had certain examples where I knew that, let's say, some 10,000 or 20,000 houses, where I knew that these were the input features. Like this house has these many bedrooms and these many bathrooms, and this was the price of the house. I already have an output variable corresponding to it, right? And then based on that, we will try to predict what if an unknown house comes. For example, an unknown house where we do not know its price, we will try to predict it on the basis of the data that we already have. We will train a model, and then that model will predict on some unknown data, some new data. So I have put up here an example of the Star Wars and Star Trek. Let's say we have two different sort of images. One, which is the characters from the Star Trek, and we know that these are the characters which are from the Star Trek. Or the another where we have, let's say, characters from Star Wars, and we know that this character is from Star Wars. We already have that information. Now on the basis of that information, we train a model, and then when a new data comes, we try to predict the response, whether this will be Star Trek or Star Wars, right? So this is what we try to do, or maybe completely something different. This is the example of supervised learning. But when I come to unsupervised learning, this is where we do not have an output label. Let's say if I give you the data of all the houses with only input features like the number of bedrooms, bathrooms, and its location, but I do not tell you what the price of the house is, right? Now you do not have any output, you do not have any labels, you only have uncategorized data. Now that becomes a problem of unsupervised learning. In such kind of learning, we try to look at the similarities in different examples, similarity in objects, and try to find out patterns and try to cluster them. That these are the group which look more similar to each other, so maybe they should be put in one cluster. Again, if I talk about some of the characters, so you will see here, I have characters from different fiction characters, but I do not know either they are Star Wars, Star Trek, Marvel Studios, whatever they are. We have no information about it, but we somehow try to cluster them, maybe on the basis of different features like how they look, when these characters were released, and try to cluster them into different. And then once we cluster, we may be able to interpret, okay, that these are the characters which were similar, maybe they belong to something like this sort of a category. Now this is the problem of unsupervised learning. Now, even in the unsupervised learning, we have two different tasks. One is the task of regression, another is the task of classification. Now, coming to the regression part. Again, like I talked about the problem of housing like predicting the prices of the house. So that becomes a regression problem because the output is a continuous variable, right? It has a lot of values. So simply put, let's say if you have certain input variable x and output variable y, and this crosses here tells you that for a certain value of x, this is will be the certain value of the y. This is your data. Now when we try to fit a line or some other curve between them, now that becomes a problem of regression, right? Where the output is continuous in nature. But at the same time, if let's say we have data where the output is some discrete, for example, let's say I give you two set of images, one is for dogs, another one is for cats. I say that crosses are for dogs and circles are for cats. Now we want to find out the line that separates the two type of data. Now that becomes a classification problem where we are trying to look for the equation of the line which helps us to discriminate from one class to the another class, right? So if you will see the difference here, we are trying to look at the some function, some relationship between input and output. Here we are trying to separate between two different classes, two different type of inputs, you can say. So this is the problem of classification. Now, as I was talking about unsupervised learning, in unsupervised learning, we have a very specific problem of clustering, where on the basis of, let's say, the distance, how close the objects are to each other in terms of their input features, we try to cluster them. Like we have no information, we do not see anything red, they all are in purple because we do not know which kind of groups they belong to. Like in the classification task here, if you will notice, we knew that this is class 1, this is class 2. But in case of clustering, we don't know anything about it. We only know that we have certain set of data points. So on the basis of this, we try to find out some sort of hidden structure in the unlabeled data, and based on that clustering, based on that, based on its input feature, we put it in some groups, maybe which are more closer to each other, which are more similar to each other, are put in the one group. So the points which are in one cluster are more similar to each other as compared to the points which are in the other cluster. So this is the problem of clustering or the unsupervised learning. Now there is a third type of learning which is called as reinforcement learning. In reinforcement learning, what happens is that the agent, it learns from its environment, in the sense that where, let's say, there is some agent and there is an environment where we have fire as well as water. If the agent will move towards fire, right, it will say, oh, okay, it may get burned, it may get hurt, so this is not the right direction in which it should go, so it get penalized for it. So it knows, it doesn't exactly know the right path, but it knows in which direction to go, where it will either get reward or penalty. It will try to maximize the reward and minimize the penalty, and based on its interaction, based on its feedback that it gets, it updates its learning policy. So most of the games that we see, like the algorithms in the automated games, for example, I talked about the Go or something, it is a reinforcement learning that is going on in the backend, where they try to see that how the agents have, like where they try to look at the many different past moves that the people have played and learn from it. On the basis of it, they understand that this sort of move should get them reward, or this sort of move will get them a penalty. So this is the example of reinforcement learning. Now when I talked about machine learning, though I have told you in general there is supervised, unsupervised, and reinforcement learning, specific algorithms when I talk about, like classifiers or the regressions, there are some. I will not go into the details, but maybe just throwing some names here so that you see them in the future, you may be able to relate it, that these are the machine learning algorithms that somebody has talked about. Like there are linear classifiers which distinguish between two classes and try to find a linearly separable plane or line. Then there are decision trees which sort of go into a tree hierarchical sort of a structure where say, okay, if the feature 1 is less than this or greater than this, maybe it belongs to class 1, and it takes certain decision at every step. Then there are neural networks, where we have taken inspiration from the neural networks of humans itself. Then there are some other kind of k nearest neighbor, SVMs, and many more. So now coming to the third part. So we now know about supervised, unsupervised, reinforcement. We have also taken a look into the classification and the regression problem. Now the third aspect is whether it is a batch learning or online learning. Now, what is the meaning of batch learning is, let's say you get a huge chunk of data. You get a data of, again, if I talk about houses, about 20,000 different houses. You use all of that data and then you train your algorithm at once on that data. So it is a case where we take the whole batch, where system is incapable of learning incrementally. It must be trained using all the available data. So it also takes a lot of time, computing resources. So we also typically do it offline. This is not the strategy that we may like to follow online itself. So what we do is we first train the system and then we launch it into production, which runs without learning anymore. It just applies what it has learned. Another sort of learning is the online learning, where what we do is we first have a certain set of data. We then train our ML algorithm on top of it, right? We launch it, then like we evaluate the solution, we launch it, and when we get new data on the fly, like there is new data which is coming up every day, right? We again learn, we again run and learn, and then again sort of launch it. So this is where we also do incremental learning or sequential learning, right? We will keep on learning from the new data in itself. This is how humans also work, right? Let's say if we see something which we have not seen in the past and somebody tells us, like if just again take the example of a kid. If you tell a kid that, okay, this is a pen, the kid may have never seen the pen before. The kid will learn, right? So the next time when you will show him or her a pen, he will be able to understand, okay, this was the pen that I had seen in past. But in the batch learning, once you train on a certain set of a data set, then you do not sort of improve your model further, which is not the case with the online learning. Now, even in the online learning, if we have a huge set of data, a very big data, what we do is we sort of chop it into different pieces, like a small chunks. We divide our data and we train our algorithm on those small chunks. Like we train the algorithm, we see how good it is performing, we analyze the errors, we again try to improve it on the different chunk, and then again we run it and we keep on repeating this process, right? So there's fast adaptation, it learns quickly, but also it quickly forgets, because you keep on getting new data, it might forget what it had learned on the previous data as well. So now coming back to the problem of the housing prices. So we saw the bigger picture, we tried to see into what would be the different type of the problems. Now we will do the same for our data itself here. So the very first thing, as I said, data collection. So this is the data that we already got from a certain resource, you can say. This is how our data looks like. It has the attributes like longitude, latitude, which tells us about the geographical location. Then we have the attributes like how old the house is, its median age, how many rooms are there, total bedrooms, population, household, right? This data corresponds to one block or the districts. Like if you will see, I don't think any house will have 1100 number of bedrooms. So it is for the total number of the houses which might be present in that block. Then what is the median income? Yeah, this is something that we want to predict. What is the housing value? So in the data, we do have this for a certain set of problems. So here you can probably see what kind of algorithm that we will be using here. So if you will notice, one, we have continuous values, right? So maybe it will most likely be a regression problem. And since we also have the output labels, so most likely it is also supervised problem, right? Because we do have the corresponding values. Like for all of these input features, we know that this is the output that we want to predict. So we have total 10 attributes here, 9 input and 1 output attribute. So the next step, as we talked about, is the data visualization, where we try to learn certain aspects of the data. So we have plotted a histogram here. Here you will see that there is histogram corresponding to all the different attributes: households, median age, latitude, longitude, right? So if you will see, a lot of them are the unimodal, like it will start to increase and then it will start to decrease, so it will have sort of one peak. Whereas other, they are bimodal or even the trimodal, right? So what does it really tells us about the data? What does it really tells us about these features? So when we have a unimodal, it tells us that on average, like this is the peak. Like most of the households maybe are around this longitudes, right? And rest are spread out at different places. But at the same time, the median housing age tells us that maybe some of the houses are around the like age of around 15 years, but some of the houses are old. They are like 35 years old or 36 years old, right? So there are two maybe different type of houses there. And when we look at the latitude, we see two different locations. Maybe they are spread out at two different places. And we can also observe here that all of these variables, they have very different scales. Like the housing value goes from 0 to around some 50,000 or 5 lakh. Number of households go from around 0 to 6,000, right? The income has some another different scale. So these are the things that we need to look into when we visualize the data. That some histograms are very tail heavy, whereas some of our algorithms require it to be more bell shaped. Then there is another sort of visualization that we do. So we see here that we have longitude and latitude. So maybe we can plot it on the 2D graph itself. So if you will see this visualization, this is a simple scatter plot of longitude versus latitude, and every dot represents a house, right? So do you think this is a good visualization? What do we get out of this visualization? Other than this, that okay, the houses are spread out here, we do not get a lot of information here. In the sense, we do not even get an information about the density, because they are all overlaid on top of each other. We don't know if they are more dense over here or they are more dense over here, right? So it means this is an example of a bad visualization, but we can turn it into a good visualization just by tweaking some small parameters. Like you will see it over here. So here you will see, based on the density, the color intensity has also changed. So maybe the darker color means these are the more densely populated areas, whereas the lighter color means, yes, houses are also here, but the density is lower. So when we visualize, we should also make an attempt to make a photo or like any figure or the visualization that give us more information. So now, in the same visualization, let's try to make it a little bit more better, right? So we saw that we have information along with longitude, latitude, and like where those are located. We had information about the prices of the houses. We had information about the population of that area. So if you will see this, you will see that we have used the color as well as size of the dots here as well. So now the size is proportional to the population. Bigger the size of the circle, more the population of that area, right? And more reddish the circle, it means higher the prices. So if you will look into this visualization, you may notice that the more expensive houses are along these lines, right? Is around this location, or maybe a little chunk over here. So what's so special about this location? Can we try to figure that out? Like our data is telling us that something is there which makes the like this location to be more appealing, where people want to pay more prices. So in order to look into this, so what we do is we further I think I have, yeah. So we further overlay a map on top of it, right? And we see that, if you will see here, that these are the houses which were closer to ocean. So it is the ocean proximity which has made them more expensive. So these are the steps that you generally take in order to understand your data, right? We started here. We started with some values that just looking at it, we could not make any sense out of it. But then we started plotting, we started visualizing, and we have now at least figured out some important correlation here, that the ocean proximity is important. Like the people are ready to pay more if they are closer to oceans, right? So it means that we can look at the further correlations as well. We can see how correlated these features are to get more insight about it. So here you see the correlation plots, right? So again, I'm using I'm using Python. So these are very standard plots which are available there, which provides you the histogram as well as relationship between different. So here, if you notice at this particular plot, now you will see that it shows us about the median house value and the median income. You will see a very linear sort of a relationship. That is, with increase in the median income, the housing value is also increasing. House value also increases. It means more people, like higher the income, more value, more price they can pay for their house, right? Seems very obvious. So so this is the correlationship that we are also getting. So we try to find out the correlationship of the housing value with the rest of the variables, and found that the median income is highly correlated with it. Then there are some other variables, for example the total number of the rooms, or the age, right? Household, bedrooms, and all of that. And it varies between -1 and 1. Now, this was the step where we were doing visualization. Now, let us try to prepare the data for the machine learning pipeline. So you will notice, ma'am, sorry, how much time do I have?
Approx 11, 11, 5, 10 you can take.
Sorry, 10, 15 minutes.
Yeah, 10 to
Okay,
15.
okay, maybe I should move more. We have a lot more slides to show. So, okay. So, when I talk about machine learning pipeline, so we need to clean the data. We need to see if certain values are missing, how they should be how they should be dealt with before training an algorithm on top of it. Like we can, if there are some missing values, we can either get rid of the whole attribute itself, or we can get rid of those particular examples where the values are missing, or we can fill in that missing value with the mean or median or something like that, right? So also we saw that there could be certain categorical variables. For example, we had here ocean proximity, which is not a numerical variable, but it is a categorical, which tells us about the near bay. There were other features like if it is closer to the ocean and that. So in order to handle those categorical variables, we need to convert it into the numbers. And there are certain strategies to it. One is the ordinal encoding, which means that, for example, here I have the variable with the different values: every day, never, rarely, most days. So what I do is I simply assign different numbers to it. Never is 0, rarely is 1, most days is 2, then every day is 3. But in this kind of encoding, there should be some sort of relationship among the levels itself. Like, for example, the never is rarely is greater than never, and most days is greater than rarely, right? So it may work, but many variables do not have such kind of relationship. For example, male, female, third gender. Can we say that the male is 0 or the female is 0? There is no relationship, right? So it creates a problem of distance. So the another option is to go for the one hot encoding. In one hot encoding, what we do is, depending upon number of levels we have, for example, in this case we had red, yellow, green, we create more variables. We create one variable for the red, one for yellow, and one for the green. And we will give value of 1 corresponding to those variables where it is true, and rest of them will be given the value of 0. So this is an example of the one hot encoding where we can convert our categorical features. So the next is the feature scaling. As we saw that all those features, they had different ranges, right? Some may vary from 0 to 50, some may vary from 0 to 10,000. Now the machine learning algorithms doesn't work very well when you have it on very different scales. So we sort of use different techniques to maybe bring them into the same range, maybe from -1 to 1 or 0 to 1, or we use another sort of standardization process. So when I talk about data pre-processing, in order to summarize it, there are different steps like data cleaning. Then we may also have a step where we are integrating data from the different sources, right? Then we are doing some sort of data transformation, like I talked about scaling with you. So here the 10 was converted to 0.1 and the 25 was converted to 0.25, right? And then sometimes what we do is we also try to reduce our data where we have a lot of features, and we try to pick only the ones which are important and then use that to further train our model. Now, in order to further train the model, what we do is we have a certain training data, right, which is the feature vector. We train it to our model. We give it to our model to train. Now, the model could be a neural network, an SVM, or classification regression model. There could be different type of models, and we get certain output from that. We have certain parameters corresponding to the models. Once we learn that, for example, if I again come to the housing prices, and if I make it simple, if this is area and this is the price, once we learn this hypothesis, once we learn what is the relationship between input and output, in this case this straight line, right, or like what are the values here. If I talk about line, we all know, we have done it in mathematics, y is equal to the ax plus b. So here training a model would mean finding that the values of a and b. So once we find that out, once we learn that, then we try our model on the test data. Sorry, just excuse me for a minute. Just 1 minute. Hello. नहीं मैम, वो सीट पे नहीं है मैम, पता नहीं, मैंने देखा नहीं मैम, मैंने टॉप दे रही हूँ. हाँ जी, अच्छा ठीक है मैम. Yeah, so once we train our data, we get our test data, right, which is, you can say that the unknown data, and we see how well our model, our trained model, is performing on that test data using some sort of performance measures. For example, if it is a regression problem, we use like root mean square error or confusion matrices. So maybe I will not go into a lot of details of these performance measures now. For example, that just to tell you the importance of the performance measures. For example, if it is a classification problem where where our algorithm tells whether a certain person is pregnant or not, so the one of the incorrect scenario could be where you are telling a man that he's pregnant, or the another scenario where you are incorrectly classifying is where you are telling a pregnant woman that you are not pregnant, right? So these are the cases of false positive and false negatives. These are the sort of performance measures, accuracy that we use for the classification problems. So similarly, for the regression problem, it is the distances that we use. It is the error which is between the actual value and the predicted value that we use as our performance indicator, like how far off our predictions are with respect to the original data. Now, maybe I'll skip this part for the cross validation as well. I'll now come directly to maybe just a glimpse of some of the examples. I'll try to give some examples in the wireless setup itself. So when we talk about, let's say we have been talking about the driverless cars, right? The intelligent vehicular network. We say that the future intelligent vehicles, which are at the heart of the high mobility networks, they have a lot of onboard sensors, advanced sensors, they keep generating large volume of data, and machine learning might be a very good approach to which can be exploited to get benefits of such kind of networks. So if I specifically talk about these sort of vehicular networks, so we need something which can which can provide connectivity between the vehicles, right, as well as which can enable like the onboard computing as well as the sensing technologies. So over many years, many different communication protocols have been developed which were dedicated towards the short range communication where the vehicles could interact with each other, but they were also very limited. So some of the recent technologies, they try to focus on they basically try to leverage the high penetration of the cellular networks, right? So we have cellular networks everywhere, where the information, one is there could be a vehicle to vehicle exchange of information. There could also be a vehicle to the infrastructure, which in this case, let's say the cellular networks here. There could be exchange of information as well. There also, like maybe the future 5G cellular networks could be used for such kind of the purposes. So in the context of this, these kind of networks, there are certain problems that can be solved. For example, what could be the, let's say, the traffic flow prediction, right? Like which route could I take in order to avoid the traffic jams, in order to avoid the congestions, or let's say like in which direction we should go, or based on what are the road conditions, based on what are the, let's say, the speed or the acceleration or the direction of the cars, can we predict that this much of traffic flow will be there in a particular area. Like we know certain very simple things, like in the peak hours we see a lot of traffic jam. This is something that we already expect, but can we do it at a bigger scale, where we can get live information from the vehicles, from the onboard sensors, which is where it is being communicated, and then we use machine learning algorithms on top of it to try to find out the optimal route. So I have a problem here for you, which is called the problem of the traffic flow prediction. Now, let's say I have now here plotted here my own institute and the network itself, and we see that the certain area Google Map tells us that there might be congestion somewhere over here. So if you will see that the traffic flow prediction problem, once it is spatial in nature, right? There could be different traffic at the different points in the location. At the same time, it is a temporal in nature. There might be traffic jam here right now, but after 10 minutes, there may not be any traffic jam. So if we want to use machine learning algorithms for such kind of process, how we do it, how we can do it, right? So let's try to frame a problem here. Let's say we have certain observations for the traffic flow. We know that at the particular time t and at the particular location, this much of traffic was there, and we have this information over the different points of time. We have this information at the different locations. So our problem is to predict the traffic flow at certain time interval for some prediction horizon, right? So let's say if this is how the traffic flow, the sequence, now it's a time series problem. So if this is how our data looks like, right? So we give this data, what we want to predict is if the traffic flow given the past historical data was something like this till the time, can we predict how this traffic flow will look like in the future? What it will look like after 10 or 12? Like, will it increase? Will it decrease? Will it increase very suddenly? What will be the kind of the patterns? This is what the problem is. And we want to predict it on the basis of the past data that we have, like on the basis of the patterns which the traffic data has followed in the past. So this is where the machine learning algorithms are used. Some of the, I'll just throw names here since we do not have time to go into the details. Some of the algorithms like ARIMA, SARIMA, the neural networks have been used for this kind of problems. And if you will see here, it tries to predict the patterns, like the one in the blue and the red here shows the predicted and the actual traffic flow which was there. And generally we evaluate the performance of this kind of algorithms using the relative errors, like how much of difference in prediction that we have obtained. So this is one of the example where the machine learning can be used for let's say the traffic flow prediction. Now I'll come to the another example, which is the problem of, let's say, the node placement for wireless sensor network. Now we know that in the wireless sensor network, sometimes we have a large number of low cost, low power sensor nodes, multiple sensor nodes. They may have very limited computational and communication capabilities. So like sometimes their deployment is random, sometimes it is very deterministic in nature. Generally in the hostile environments, let's say hazardous area, battlefield, their deployment may be random, right? So these sensor node, one of the very important concern is energy utilization. while we want to maximize the information which is being conveyed, we want that they should be using the minimum energy, because it may not be possible for us to like replace the battery or recharge it all the time, right? So how do we minimize the energy at the same time get the maximum performance? And we also want to take care of things like the network density. What if there is failure in one node? So the network should be dense enough so that so that the another nodes are also present in its vicinity and they can communicate the information, right? Then there could also be issues of the network connectivity. We want a longer lifetime for the network, like what kind of communication protocol which is being used, that is also to be taken care of. So in these kind of problems, I'll design one problem here, a hypothetical situation, and then we will try to optimize, like we will try to find the nodes, what could be the operational modes of the node to meet the specific application, along with minimization of energy consumption by the network, like how the sensors should be placed, which sensors should be active, which should be inactive, because we want to save the energy. If we keep all the sensors active at all the time, then that's also a problem. But at the same time, we want that there should be enough information which is being conveyed. All the information is being conveyed, right? There should be proper connectivity. So I have in front of you, you can see a grid-based wireless sensor network layout, right? This is like a sort of a grid where at the intersection I have placed different sensor nodes. Now there are three different colors, if you will notice. The three different colors mean there are three different type of sensors, and they are, let's say, monitoring three different parameters. One is monitoring temperature, another is monitoring pressure, or some other hypothetical parameter that you can assume at this point. So what we want is, and some of these sensors, they have the capability to communicate to the central node. Let's say the blue ones here, let's say we call it the X node, they have this capability that they can be in charge, whereas the other sort of sensors, Y and Z sort of a sensors, they have very medium or the low transmission range, whereas X have the highest transmission range. So they are the ones which will be communicating information to, let's say, a central node, right? So how do we decide which sensors should be active, like in this, how do we make clusters of them so we are able to communicate all the different sort of parameters, right? At the same time, minimize the energy utilization. Now, because since X has the highest this has the highest communication range, it also has very high energy requirements as well, right? So let's say again, this is some, and we are trying to optimize certain parameters like its coverage, if there are sensors which are out of range, what is the network energy. So let's say a different sensors, and based on what kind of a sensor, if you want it to be active or not, or in which mode we want to operationalize it, we have given a certain sequence. 00 is inactive, 01 is X mode sensor, and we define these sequences for all. So what our purpose is, how do we set this sequence so that we can get the minimum energy requirement and maximum field coverage. So these are some of the objectives that we want to fulfill. So I used a certain optimization algorithm here. So as a result, you can see like this is one of the layout. This is one of the layout which tells us what will be the different modes of the sensor, and the crosshair tells that in the certain configuration, you can make these sensors inactive in order to save the energy, right? And if you will see the algorithm, the machine learning algorithm which was used, it has increased, like over the time, it has increased the fitness value, which basically here means it has tried to find out the optimal energy requirements, right? So maybe this is where I will end for the time being. I have skipped some of the slides because of the time restrictions, but I hope it's just not too much. So thank you, everyone. If you have any questions, please feel free to ask.